Welcome back to episode 4 of this CNC plasma build. So in this episode we'll have a look at the parts we need for the gantry. We'll get some of them trimmed down to the right size on the CNC machine. Then we'll have a look at these cheap rails and just see how straight they are within the best of our abilities in this workshop. And then finally we'll put it all together and get some motion. Welcome back to the workshop and welcome to episode 4 on this CNC plasma machine build. In the last episode you saw me make a modified Z-axis, so I'm a lot happier with that. And we also got some movement out of it using this little stepper driver. So in this episode we need to get on to making the gantry. As you can see underneath, I've been busy cutting out some of the aluminium box section. Okay, a while back I ordered 3 meters of this rectangular section, so it's 80 by 40 by 2mm wall. And I think the whole lot came to about £65, so it's getting quite expensive for the material. Anyway, while I was chopping out the gantry, I thought I'll chop out the other bits as well. So we've got the main base there, which will be on the bed, and then there's a lower reinforcer that's below that, so that's 900, that one's 820, and then the bit we need for the next step is the X-axis gantry, which is at 700, or 697 if you mark it out and then cut on the wrong side of the line. Yeah, I was not pleased I did that, and the bit I've got left over isn't long enough. So a couple of options. I could buy one that's about 800 long, just in case, because they do sell it in 700 as well. 800, mark it out, cut it to 700 long, and do it that way. I think it was about £15, but this is just eating into the budget. Or the other option, because it's not super critical how long this is, what I've decided to do, because I'm 3D printing end caps that go on the end of here anyway, I've just got one. Instead of 3mm, it's 6mm thick, and it just takes up that extra so that the rails finish at the edge of this, so it's more cosmetic. So I think we'll go with that option, and in future I'll double, triple check. It was the first one I cut as well. The rest, obviously, I was really careful. So those are reasonably accurately made, although their length isn't super critical. But the ones that are, I've got 2 upstands here which are 40mm, and that distance there dictates where one of the beams goes, and it's reasonably important how accurate it is. So I've just been over on the CNC machine leveling this, so I overcut it slightly, and then I just machined it down till it's 40. In fact, just get the I've done this one, so let's just see. I think we're about 0.05 over. Try and get it to line up. There we are. 0.05 on that corner, and on that one 0.04. And we're bang on there. Trying to get to pick up properly on the surface. It's quite thin walls, it's hard. There we go, and 0.05 there. So I'm going to leave that. I think that'll be okay. So we've done that one. We've got this one. As you can see, it's rough cut off the saw. I've just tidied it with a file. Let's go and bring this one down to size. So essentially what I've been doing is finding the surface that's sort of flattest, and I've got 2 parallels in here. Pop it up, got it nice and clean, get that down on there. Tightening it up, make sure it's seated. And then doing a minimum cleanup on that, tidying it up, turning it over, and then bringing it down, and I can check how we're doing by getting in under there. So see 40.85, so we've got just under 1mm to take off. Cut it a bit fine, didn't I, with the saw, but anyway, there we go. And 40.65, so not much to take off. Probably should have left myself a little bit more, but anyway, let's see how we go. We'll clean this up and then dress it with the file so there's no burrs, turn it over and come down to that final dimension. I think the next thing to do is to mark this out where the linear rails are going to go. I've got the drawing for the whole thing there on all the different sides and the holes, but it's quite hard to see. Okay, to make it a bit easier, I've zoomed in on the detail, so we need to drill and tap these M5. This is for one rail, and that's for the other, and that's 16mm in from there and 64 to that one, using this as our datum, and then it starts at 20mm in. So I'll go to the surface plate, mark this out, and then we can start drilling and tapping. Okay, the part's obviously a bit big for this, but we should be able to do it by sliding it along. So if we want to go 16mm in, put the lid on the floor. And then we've got our 2 lines marked. So it's pretty handy having this surface plate. That's not a surface plate. Okay, yeah, it's not a real surface plate. This is a marble hearth off an old fireplace, and it's about the flattest thing I've got in the workshop, so it's got to do for now. Now this should be 6mm from here. Yep. So this 20mm rail, supposed to use these M5 cap head screws, and you can see obviously the head fits nicely in there with a little bit of clearance. But that hole down there is 6mm, so there's quite a bit of adjustment. Alright, one down, I don't know, about 12 to go. Okay, so we've got the rail roughly lined up. I'm just going to line it up to the edge now. This side piece here needs to be 6mm away from this. So I've just been using that bit, which I don't use very often with the calipers, but you see there's like a step there. And what you can do then is so pretty good. So I've just tightened this one up. I've just checked the other end as well, and it's pretty close to 6. So it's good enough for here. So we'll mark this out now. What I'm going to do, I've got a couple of approaches when I do rails. You know, you can use like little guides, drill bush guides and things. I think this time that is an amazing fit. There, like that, on a 6mm spotting drill, just like that. So what we'll do, we'll just I've already got a line down there mark that I showed you a minute ago, and we'll just spot that out, do that all the way along, take the rail off, go to the drill press, which is just here, and then drill them out properly. What we're going to do this time as well is use this rail as a reference to get this rail on. Yeah, we're not after, you know, CNC, router CNC type precision here, I don't think, with the plasma, so I'm happy to use this rail. We'll make sure it's nice and straight, and then we'll make sure the other one is parallel to that. I'm trying to get it parallel to this edge. I don't know how straight, flat this is, but it's all we've got to go on, because ultimately, as long as these two are parallel to each other, this is adjustable. So the arm sticks out, but I've got adjustment like that, so I can get it nice and square and get that dialed in, and that's ultimately all that will matter, but that will come later. For now, we'll get these pretty close, and then that gives us a fighting chance. Right, let's drill this out. When I say drill it out, I mean just spot it. Just make sure the clamps are nice and tight. Double check that. Okay. Okay, so we set up in the drill. I used a pointed end just to get it centered over there. We zeroed off, and we've got our 4.2mm twist drill ready to tap for M5. Now, I've got nowhere near enough travel to do all that, so we'll just do a few of these, and then we'll just increment it along and just repeat, pick up off a hole again, and then repeat there. So I think that'll be good enough. Right, let's drill this out and then get tapping. So I could just obviously drill all the holes and come back and tap them, but because we're not going to use the DRO, because I'm going to have to move this along, we'll do it like this. I think it'll be fine. Won't take very long. Okay, so I've just drilled and tapped all the holes for the first rail, and then you can see I've just opened up some of these where the stepper motor will go. There's a limit sensor thing there, and there's a couple of holes the other end as well on this side. I'm just drilling these out. These will be clearance to get the socket tool through, because we've got to get access to these bolts that fix this to the plate. So we'll drop this all the way through, and then on the other side we can open them out to the final size. Okay, quick update then. So we've got all the tapped holes for that rail. We've got some holes down here which will be for the ball screw mount, and then that's for the limit detection. We've got a homing detection little thing that goes on there, and then the stepper and the drive unit will go here, and the ball screw will run along here. So I think what we'll do, we'll get this rail on, and then we'll get one of the carriages on. We'll have a little look at that in a minute, and then we'll use that. We'll get that pretty straight along one edge. That should be about 6mm away, and then we'll use that to dial in this, and then when that's clamped down, we'll drill and tap this rail, so those two are parallel. The other thing I've done is just got some clearance here. I'll put it away. So essentially that hole goes all the way through, and there'll be 3 of these are M12. You have to imagine they're inside the section. 3 of those that will bolt it onto a plate, and that'll allow me to sort of get this 90 degrees, so I can adjust this slightly, and then that's to get the Allen key through there, so I can actually get it into the head. It'll all come clear a little bit later, so I think for now I'll get the rail on, get it adjusted. Okay, I've just taken a number of measurements just in this gap here between this surface and this surface, a couple of points, and it's within about 0.05, so it's basically about 6mm. Given this extrusion, I wouldn't rely on it to be totally straight. Probably suggests that the rail is reasonably straight as well, at least from that sort of crude test. I didn't have to force the rail in, it just seemed to line up quite nicely. So while we're here, we'll just have a little look. Yeah, you can see obviously they ground this surface. This is not a reference, it's just clearance for the carriage to slide over. Just needs to be reasonably flat so this forms a nice seal, but it doesn't perform any other function. You can see there's a few dings here, which is, I've seen that on other rails as well, which must have been done during transit, I guess. It was reasonably well wrapped, but I suppose they can bash into each other still. I haven't really got any way of double checking the hardness. I guess once we use it for a long time we can report back on wear and things like that. The key surfaces are these ones here, so that rounded one there, one down there, and same the other side. Basically the ones that all the balls, the recirculating balls run in. So that's the key one to be hard at least. Yeah, so it went on okay. So I think what we'll do now, we'll get the carriage on, and then we can use that to align the rail, and then put the y-axis on, and then get this drilled and tapped. Okay, so here's a close look at the carriage then. Now, they don't usually come with this cable tie on, but they do have that plastic retainer, but you can see that's quite loose in there. We'll take that out in a minute, but that's stopping all the balls falling out, and it's okay when it's in the bag because the retainer can't really come out, although it does look like it could probably move a fair bit. But anyway, obviously it can't move enough. Now I've got it out, got that cable tie on because I've been sort of handling this and just having a look at it and make sure. So you've got a ground surface there which you can use as a reference to dial in. Maybe we'll just offer that up on the surface plate and just see how flat that is. And I've got, I guess those are M5 tapped. This is supposedly interchangeable, or at least definitely the same size as a high win system. And you've got your end caps there for the recirculating balls to go around. I don't remember these being on the high win, this sort of little screws and this plate bit here. I don't know, it just doesn't quite feel as quite nicely made, but ultimately, looks like I got a little mark there. Is that 1.4? If that's the size of balls they had to use to tune it in, who knows. Yeah, but ultimately all that matters is when it's on there, how well does it move and how straight, and how long is it going to last. So some of those we might be able to find out soon, some might take a bit longer. Right, I think there's not much else we can really do with this. Let's get this aligned. So I think I'll put the ground surface on there, so that's going to be out. Yeah, that's going to be outside, or I suppose positive Y. So I'll put those there. That means the grease nipple will be off to this side. Yeah, I think that'll work. So we'll clip this off, and then I've got to very carefully push that on there without the balls coming out. So let's do that next. So I've just got a bit of inverted sticky tape, sort of bouncy and captive, and we've got a little dam around there. I'll just finish that off across there, just in case. I'm sure it'll be fine. Alright, I was going to put it on that way. Okay, we just got to line it up. Okay, so we've got that rail screwed down now, we've got the y-axis bolted to it onto the carriage, and that moves nice and smoothly. And then we've got our second rail here. This is just loose at the moment, it's just clamped in place. And then we've got one of the carriages on there. And you can see they kind of move okay. They sort of stick slip a little bit, but as soon as they've got some load on them, no problem at all. And then the other thing in terms of accuracy, so in terms of the ground position of those two there, it goes on quite nicely. It's just touching. So what we'll do, I'm just going to use the method where I use this rail to get this rail aligned. But before we do that, before we connect this up, I'll try and do a quick test just to understand just how straight this is. And what we'll do with that, I was going to take it over to my surface plate. It's not a surface plate. Yeah, okay, it's not a real surface plate. But because we only want like a line contact, we're only looking at the parallelism sort of this way and seeing how straight it is. We can actually do it on the worktop here, and I'll find the flattest, straightest thing I've got to reference off, and we'll just see what we find. Okay, so this is my kind of metrology section, if you can call it that. We've got a few DTIs up there, some angle plates, height plate, and then the micrometer there, and then some gauge blocks in that box there. And then this is my plate, surface plate. As I mentioned earlier, this is off an old fireplace. It's reasonably flat, but I think for this test we don't need it to be that flat, and it's not that big. So we'll do it over on the table. And then in this little drawer down here, we have our 300mm by 300mm engineer's square. So we'll get that out and set it up and see how we get on. And yeah, it's quite heavy. So there's actually an engineer's level, so it's got very accurate gradations down there, and then it's got some kind of coarse leveling bubble in there. So I used it for setting up my CNC machine. You might have remembered it from that video. But another nice thing is, so I think so it's claimed to have a really high accuracy. I think it's 0.02 millimeters per meter, something like that, for each of the divisions. Anyway, we're going to use it for how flat these edges are. They are ground flat. I don't think they've been scraped, but it looks like they've been precision ground. So we're going to lay it on its side and just use it as an edge reference. Okay, I've got it pretty close, so it's 0 at this end, and then as we go along, get about 0.03, then it comes back, run out of travel, but back to 0, so about 0.03 bowed. Now, it's possible, I guess this has got a bow in it, it's possible that when I put this rail down, I just roughly marked it from this edge, but I didn't force it, I just got it to go wherever it wanted to go, so it should be the straightness of the rail as delivered. It's about 0.03 over the length I can measure. So we'll just try a different side of this, and then think about if I want to do anything about that. It's quite small, or I could just loosen these off and see if it naturally springs into another position, and just try it loose and just see what happens. In fact, I'll do that first. So what I'll do, I'll just loosen. About 0.02, back to 0, so it was there. So if I push that rail, can I move it? Yes, I can. Saying about 0.03. So I've been going backwards and forwards trying to adjust it, and I've loosened everything off, and I can't get it any better than about 0.03 to 0.05, which maybe for a CNC plasma is okay. One thing I've kind of noticed is, obviously we're only as good as the top of this box section, because as you pull that rail down, it will pull it onto that profile. So in other words, if I just press here, it's going to twist that box section. You can see I can move the needle quite a bit. I'm only on the first carriage as well. So any kind of undulation in the surface of this extrusion, which is not ground, will reflect in the rail. So probably we'll be losing that battle. So I'm just going to play around with this, get it as good as I can with the setup we got here, and then we can dial in this rail and then drill and tap that. Okay, I've made a few adjustments. I've even turned this round and dialed it in again, and get the similar kind of effect where it wavers around a little bit. So I haven't zeroed it, but you can see it's on about 65 there. It wavers around a bit, but we get up to 70, so about 0.03, 0.04 as before. So I think we'll go with that. As you can see, if I just just move this or twist it, it's only on one carriage, only on that box section, just lightly clamped to the desk. It's probably as good as we're going to get. Right, we'll tighten all this up and then we can get the other rail dialed in. Okay, so there it is. So we've got both rails screwed down and aligned, and yeah, moves nice and smooth. Okay, in case you might have spotted it, I actually had this on backwards when I did the other rail, so I've just swapped it all around. That's why I've just put that rail in at the back. I just realised at the last minute, because they need to be flush this side and slightly overhanging that side, so the y-axis needs to hang over this way. Anyway, minor detail I've corrected. You can see the 3 big holes here. I think just about, yeah, that's what will bolt on to the x-axis. And so what we need to do next is get the stepper motor and the ball screw, the ball nut on there, and the little bearing, and get all that hooked up and see if we can get it to move. Just taken the ball screw off because I forgot I haven't put these on. So these will be for, this is for the home, so the proximity sensor will sit in there, and then when it slides along it'll detect on that, and then this is for the end detect when you got to the end of the axis there. So they're 3D printed, they're adjustable both ends. That's about where I think the home will be, and then I've just got to press in a little steel disc or aluminium disc, and that will get detected on that, and then we can put the ball screw back on. Okay, to put the stepper motor bracket on there, these are through holes, because this is quite thin, it's only a couple of millimeters. So I think I showed this earlier, but I've got a little plate here. I'll just stuck it on the back there with a bit of tape. The idea is we'll feed it in through there, hopefully, and then get it lined up like that, and then we'll bolt it through. Okay, now I'll bring in the motor mount, and I'm going to do this. I think shorter bolts would have been a good idea, but they're on order. Okay, so as you can see, we've got the ball screw mounted in, the ball nut, and then the guide at each end, and I've just hooked it up to the motor, so that looks like it's going to work. I've also got the home sensor in there and the limit one over on this side, and that'll allow me to put the little proximity sensor in there, and then when it gets over to that point it'll home, and over here it'll know it's at the limit. And you'll notice I haven't got the stepper motor back in here and the belt. We'll do that in a minute. That's because I want to have another look at the Z-axis over here, so we'll spin this round and show you what I've got in mind. Alright, so we've turned it around so you can see the Z-axis a little bit easier, and you might remember I wasn't too keen on the fact that these, once this plate was put on here, onto there, kind of stuck in place, a little bit of stiction in there. And what I think is going on is, obviously these are 3D printed, and the precision of those holes and that hole spacing in there, it's not quite enough for the precision we need to run in this bearing. I'll try and show you what I mean. So if we just put, if it'll let me put one in, let's try it that way. So obviously we've got one in, so that's not over constrained in any way, and you know, go up and down and fall down under its own gravity, no problem at all. And if we then try and put both in, well, you might even be able to see it now. So that one's in, and you can see that one. It's extremely close, but it's just, I can actually sort of force it in like that, but then it's kind of putting a tiny, not much, but tiny bit of preload on this, and then when it goes, oh, I need to tighten that up, but when that goes up, oh, let's just tighten these. Oh, I've taken the screws out. Oh, okay, well, I'm not going to reenact it, but basically you get the idea. If I put those screws in there and tighten it up again, it was putting enough load on, so essentially it was causing one of these to kind of stick up in the air. Yeah, like that. So what are we going to do about that? Okay, well, to try and get around the fact this is 3D printed, I've remade this. So as I mentioned earlier, I've now remade it in aluminium. We've got our little studs in there as before, and yep, that all looks good. And then we've got our kind of pinch bolt arrangements there, and they go into there. Again, this is very precisely machined because it's on my CNC machine. I trust it probably more so than the accuracy of the 3D printer. But again, you can see if that is a nice fit in there. It is very close. In fact, let me do it the other way around so you can see a bit easier on camera. If I get this one in, oh, it's not easy letting me doing it, but it is very close. But you may be able to see there's a very small gap. Again, I can force it in, but it's putting preload on. So I've had another idea, which I think essentially what I want to be able to do. This is fixed. I want to be able to fine tune that spacing. Not much, but just a tiny amount. So I've come up with this idea. So I've reprinted that block. Again, we've got the same holes down there, same pickup for the ball screw and for the proximity sensor. Since I'm reprinting this, I thought I'd put some little housings there that hold these springs that will give me a little bit of preload just to definitely push it away. The other thing, it's now in two pieces. So essentially what that'll allow me to do is screw that on there, and then it shouldn't need much, but some tiny adjustments like that of the other one will allow this one to run true. And then you know, it doesn't really matter on the proximity sensor, wherever that is, yeah, because it will go in like that, and it'll have, oh, I can't hold it, I'll have a nut above and below once this is in position, so that will fix in okay. And then I'm hoping there's enough tolerance on the ball screw nuts that go in there, because we're not talking much, it's really small, so something like that. Right, so I think what we'll do, we'll get this swapped out for this, and then we'll see if it's any better. Alright, so there it is swapped over, and you can see the gap there. I think I left a millimetre, so I basically took the old design, cut a millimetre slot all the way through it, extended the ball nut carrier at the back, because when I put the slot in I lost the mounting hole, so it picks up off slightly different locations, but it's the same thing. Everything else in the same location. As I mentioned earlier, took the opportunity to add these little bits just in case I needed some springs, because I got loads of these that are 9mm, but the 12 I'd either have to make my own or buy them, and they're quite expensive individually. So I think that is really nice. I can adjust the tension, I can change springs out, I can, you know, move these collars down if I want to get it like really tight and use the tighter part of the spring range, whatever. So lots of tuning options there. And then we need to make sure we can still get our proximity sensor in there. I'll just put it there for now, and I want the barest minimum of movement, really. Oh yeah, that looks like that's going to work quite nicely. Okay. And then I might have mentioned earlier in this video or previous video, this is for the wiring. There's going to be like a tube carrier here that will allow it to sort of flex up and down, and then the cover that goes around here will have a shield around that bit as well, so should keep all the wires out of the plasma. But just for now, just because we're mocking it up, I'll feed that through there. Something like that. Okay. Right, looks good. I won't put the base on that holds the torch. It'll just kind of get in the way with the rest of the build, but we know that's going to fit, and we know there's a proximity sensor obviously got to go in there, which is the detection for the collision. All right, I am, yeah, very pleased with that. There's no stiction, it just moves, and I can adjust the tension. Perfect. So I've got a design I'm much happier with. It's awful lot stiffer as well. If I kind of tap this, it just, if you can see, it's just kind of moving the whole thing as one. If I try and hold this back, yeah, that's all moving together. Before it was pretty flexible with that on. So the only 3D printed part really is this bit, but of course I've got the bearings in there, and then it's mounted directly. So the amount of plastic, if you like, between the bearing and this bit is very minimal. A lot of this is just bracketry on the outside, so it's a pretty short direct connection, and I think that will probably be okay for what we need it for. What's the other thing I was going to say? Oh yeah, so I think possibly an even better design would just be to use these round rails as the main rails that move the whole thing up and down. So imagine these longer rails like that instead of these linear rails like that. So have those long rails, have the main unit at the top moving up and down, and then have the floating unit also on those using the same round bearings, and then just have the spring arrangement between them, so sort of have the two bits like that running on the same round rail at the back, nice and compact, and then the sort of light touch off, it's just relative movement between the two. But because you got the ball nut here, it would probably end up being, you know, stepped out like this, and these rails do need a little bit of space to come out for the mounting and for the bearing to go round, so maybe wouldn't save a lot of space, but it possibly is a little bit neater and a bit simpler. Anyway, very pleased with that. So I think we're ready to put the Z stepper motor back on again and tension up the belt. Okay, I thought we may as well hook up the axis and put some power in and see if we can get it to move. So if you saw the last video, you'll know what this is, but just in case, this is a little stepper driver unit I bought off eBay. Again, I'll put the link in the video description just down below. And you put 24 volts in, and it gives you step and direction out basically into these. And then you've got on off, we've got forward and reverse, and then we've got a fine speed control here, and then you've got coarse speed adjustment on there. Again, if you look at the description, you can follow exactly how it works. And then this will put pulses out through the motor and should move it along. Now, I had quite a lot of comments in the last video because I said, why does the on-off switch not work? And I hadn't put the enable in because I never use it on most machines. Typically, you can get away without using it. So I didn't use it here. So let's see. Now I've hooked up the enable, if the on-off now actually works, because if you don't do that, it slowly creeps along at a very, very slow speed. So let's switch it on and see what we get. Alright, so the green light's on there. We've got a red alarm, and I've got that button pressed in, and the motor's not turning. So if we release it, and now it is. So kind of works in the opposite sense, but anyway, for those of you who commented, maybe the enable is what that is running. Yep, that's correct. So when you press on, that must be putting 5 volts in there and sending an alarm. Anyway, we can now turn it on and off, which is great. Okay, well let's move it along slowly. Which way is that going to go? This way. The other way. Oh, that's maximum speed on this coarse setting. Yeah, that's good. Okay, I've just swapped the jumper over onto the maximum speed. Let's see what happens. We'll turn the power on and release the enable. Oh, that is minimum speed. Oh, okay. Go back the other way. Yeah, we're overloading. That's probably about as fast as we can go on this current setting. Okay, I've just turned the current up on the stepper driver from 1 amp to 2.8, so it should be nearly 3 times as much. Hopefully get a little bit more performance out. So let's switch the power back on. Okay, and then enable. Be careful it doesn't crash into the end. And a little bit faster. Oh, and it's just tripping out there. Probably because we're only running it on low voltage with 24 volts, so we could probably do a little bit more. And we can probably go, I think this motor will run just over 3 amps, so we can bump that up again. Anyway, we've got a nice smooth motion. That was the main purpose of this, so yeah, great progress. Okay, I couldn't leave it there. I've done a little bit more experimentation, and essentially it's stalling out when I reverse direction, and it's probably because it's getting loads of pulses in one direction and then it's instantaneously going the other way. And normally you'd have a little bit of deceleration and then acceleration, even if it's subtle. Otherwise you get that problem. So if I now, now enable it, and I'm on the slowest setting, we can reverse, no problem. In fact, let's give ourselves a little bit more space. Obviously there's no end detection at the moment, so I've got to be a bit careful. Right, and then we ramp it up, we can get quite a bit more speed. So the issue is just turning round. So if I slow it down, here we go. Well, until that happens. Anyway, it's certainly going an awful lot faster. Let's try one more. Alright. Basic concept working. Alright, really pleased with progress so far. I'm glad I made that out of aluminium. That's a lot stiffer and a lot sturdier now. Also, it was worth making this in 2 pieces to get that fine adjustment, and now it's really smooth. Obviously on super thin materials it will still bend rather than touch off. It might interfere with the torch height control a little bit, but it's a lot better than it was. We've still got the option of adding like an external ohmic sensing as well as like another way to do it, but let's see how we get on with this. Very pleased with the Y-axis motion. That all went in with no real issues. Obviously it's running a little bit slow now, but we'll just get the correct voltage and get the proper drivers in there. Hopefully that'll run a little bit quicker than that. And yeah, we've got the Z-axis back on again. That's all working nicely. We showed that in the last video. Yeah, and it's really starting to come together. So I think that's it for this video. Hope you've enjoyed it. Thank you very much for watching. If you want to see how this turns out, feel free to subscribe and click that bell for notification when I get around to uploading another video. And with that, we'll sign off and say thank you very much for watching, and see you next time.